Hello everyone, we are Anthropolite Robotics 2024 team and we are presenting our robot cars. I'm Victoria Grigorieva.
I'm Jody Schuster.
I'm Jose Enriquez.
I'm Jair Sanchez.
And I'm Jacob Bollinger.
So it's our customer, Anthropolite SoutheastCon 2024. It took place in Atlanta, Georgia from March 20th to March 24th.
Here is a picture of this year's competition field. We started in that gray box at the top, picking up the large and small packages and delivering them in their respective areas. The large packages go in the blue zone for 3 points each, and the small packages go in the red zone for 5 points each. We then pick up the fuel thrusters and take them across the crater by either using the zip line or creating a bridge. And then we assemble we get 20 points for going across the crater and 20 points for then assembling the fuel tanks in their thrusters. And then we have team promotion for 10 extra points before completing the course in under a minute and 45 seconds for 30 points.
Here's our initial Gantt chart for our planning. As you can see, our research phase started at the end of August and we went to the beginning of October. Then we moved into our design phase, which went through October through December. And then from there, we go to our build phase and our testing and redesign phase. But over the winter break and into the winter semester, we had some issues come up, so we had to redesign. And all that did is really push our initial build design back a little bit into our testing phase and redesign phase, which didn't affect too much.
So our project overview can be broken down in like 5 different stages. The first one is a mechanical build, where we chose circular chassis, and that was for the ability to zero turn around the field. We also, for crossing the crater, we picked a bridge over a zip line, and we used our robotic arm. For the electrical build, the 3 main sensors we used were the ultrasonic sensors, the IR, and the encoders. For team promotion, we used an LCD screen. For microcontrollers, we used the Jetson and the Arduino Mega. And for the power systems, we used 3 LiPo batteries. And continuing the project overview, our CS field was a trained AI model, the navigation across the field, setting sensor parameters, and programming the arm. For our collection mechanism, we used the robotic arm, storage mechanism, object detection, and the sweeping mechanism. And some restrictions with our project was it had to have a weight limit of 25 pounds, a size limit of 12 by 12 by 12 inches. We couldn't, no projectiles, so no throwing things around. We had a 3-minute limitation, and we couldn't leave any residue on the competition after each run, so we couldn't fill the crater with sand, for example. And also had to be completely autonomous, no Bluetooth, no Wi-Fi, no outside interference. So the first thing was a mechanical build, the chassis. Initially, we were just gonna use 1 level, but when we got into the building phase, we ran out of space very quickly. So we solved this issue by adding 2 layers on top of each other. And as you can see here on the second level, we have the robotic arm, the storage container, the safety button, the team promotion. And on the bottom, we have the ultrasonic sensors. We have all the microcontrollers and the voltage regulators. Continue with the mechanical build. So we chose a bridge over using the zip line. So some pros with using the bridge was easier to implement. There was no electronic components, and it was cheaper to build. So cons using the bridge was it was a little bit less accurate, and it took up more space on the robot. But considering the both, we ultimately decided to bridge over the zip line. The last thing for the mechanical build was picking the wheels. So for our competition, we had a ramp that was 22.5 degrees, and that was our objective. And we decided to use a 4-inch diameter wheel to keep the restriction of 12 inches in total. And we assumed we wanted a velocity of 1 foot per second and an acceleration of 2 seconds to get to max velocity. And taking all that into account, we found the torque that we needed was 2.35 newtons per meter. And this was our last tires that we decided to use. It was off-road tires, and they provided the most traction on the field.
To begin our electrical build, the microcontroller system, initially we wanted to have a master and slave configuration. This would work through UART communication. The master would be the NVIDIA Jetson Orin. It would hold software for object detection as well as calling the Arduino functions. The slave would be the Arduino Mega. It would interact with the hardware and integrate the hardware with the software. Our final design consisted of the Arduino Mega. Like I said, it took care of the hardware integration, and it as well held the competition run software. For environment detection, to be autonomous, the robot needs to detect its internal environment as well as its external environment. For internal environment, we were primarily concerned with the distance the robot has moved. For that reason, we chose to use Hall effect encoders. For the external environment, we were concerned with the competition field parameters. For green light start, we used the photo transistor. For yellow line and crater line detection, we used the IR sensor module. And lastly, to detect distance from walls, we used the ultrasonic sensor.
So for our power systems, for initial design we were going to use two power sources. One power source was supposed to be 22.2 volt battery for motors, and separate power source, two 11.1 volt batteries connected in series so we can gain 22.2 volts. And it was for components for Jetson Orin Nano, Arduino Mega and hardware circuit. So to gain the necessary voltage for each of those components, we were using 3 separate voltage regulators. And for our final design, so we switched to using of 3 power sources, as we had some issues with voltage regulators. So we moved to using one 11.1 volt battery to hardware circuit, and we had to use also voltage regulator to drop the voltage to 5 volt, and another 11.1 volt battery was for Mega and Jetson. And also the reason why we had to use separate batteries for motors and for all the components, because motors could draw too much current, which would cause some problems with using of Jetson and other components. So for our voltage regulator, initially we were going to use LM317, which is adjustable voltage regulator. And what we had the issue with was the current draw. The maximum current output which we were supposed to get was 1.5 ampere, but the actual maximum current output which we were getting, it was 200 milliamperes, while we needed the maximum of 1 ampere. So that's why we switched to using one voltage regulator, and it is a fixed voltage regulator, LM340. It was giving us the necessary 5 volts of the output, and the maximum current which it was supposed to give us, it was 1.5 ampere, but experimentally we found out that it was giving us 2 amperes, which was more than enough for us.
To finish off our electrical build, for our team promotion, we used an Arduino LCD screen. We had it coded to show CBU IEEE robotics right before hitting the stop timer. During testing, we had some errors with the display showing random characters or showing nothing at all. We had to add a resistor to reduce some of the noise and interference from other components to get more accurate results on the display.
Alright, to begin our collection mechanism, it consists of a grabbing mechanism, which is basically a robotic arm. It has 4 degrees of freedom, a gripper with 180 degree of travel, a wrist with 180 degree of travel, a shoulder with 180 degree of travel, and lastly a base with 360 degrees of travel. Continuing, we have a storage mechanism. This mechanism is simply a container that is locked into place and unlocked by a server horn. This container is to be deposited by the arm when in the package delivery zone. Software side of this mechanism, it consists of basically 3 functions. Solve by K function, which coordinates can be inputted, and in return the inverse kinematics angles are returned. Move to angle function, which simply writes the given angles onto the server motors. And lastly, the update position function, which contains several conditions that allow for repeated movements to be possible. In addition, other aspects We added servo easing library. This allows for the speed of the servos to be controlled. This further reduced the current draw. In addition, we had to add offsets to the software side so that inverse kinematic angles could correspond with the actual angles of the servos.
Now, to pick up those objects and get those positions, we initially were going to go with object detection using machine learning. Specifically, we were using PyTorch and its vision library, Torch Vision. Initially, we were going to use ResNet 30 as our baseline model, but it was a bit too slow, so we went with ResNet 18, which is a bit faster. On top of that, we trained it further on about 6,000 images or 6,000 annotations, which were across 5,000 images. Here is the statistics of the model. As you can see, the line goes up over time. Our best model appeared at roughly 275 epochs or training sessions. The upper orange line is our mean average precision for 50%, and that hit at 80% accuracy towards the end. And the lower red line is our mean average precision from 50 to 95%, which hit 60%. Now, here's a video of what the output is from the model. As you can see, it's drawing boxes around the packages, and they are correctly labeled. The jumpiness is due to the accuracy level we have it set to currently. We could decrease it to make it less jumpy, but then it's going to have some false positives. And as you can see, the jumpiness does get better at certain angles, which is the angles we are expecting to pick up the objects at. There is also, you'll notice, let's see if it does it right there, there's a small package detected in the back, but that wouldn't affect us here because we're not looking for small packages. And then here you see again, it's jumpy until you get to right where you would be needing to look at them, and they're perfectly clear.
All right, so that was plan A. Unfortunately, it did not work out. There was issues with integrating the navigation and the collection mechanism together. So that's why we came up with a plan B. We call it the sweeping mechanism. The basis of this mechanism is we had these small packages that were placed randomly in front of the aerial travel of the robot. This messed up the robot's orientation. So physically, mechanically, it consists of a cardboard skirt that is underneath the robot's chassis. The robot is programmed to move forward and move back. When it moves back, it picks up a sweep, which is simply a foam block. Software side, the arm grips the foam block, as seen in the left picture. It moves to the set position, as seen in the right picture, and it repeats this movement 3 times. Thus, no small packages are in the way of the aerial travel.
So this is a video from one of our practice runs in Atlanta, and here we can see it picking up the large boxes. And we opted to only pick up 3 out of the 5 boxes because we're trying to save time to get it under 1:45 to increase our points. So it wasn't worth to pick up these boxes. Here we see the skirt on the bottom of the chassis pushing these small packages over here so it doesn't get stuck under it. And this is a sweeping mechanism, just kind of sweeps it out the way. So yeah, ideally there we would want to pick them up and we had a separate container over here for that, but that didn't work. So that was our plan B. And here it is going down the ramp. Here it's using that ultrasonic sensor to find this distance from the wall, and it switches to the line follow.
So here it drops off the whole container, and it was allowed by rules just to drop the whole container instead of dropping off one package by one package.
Yeah, then it goes back to the line follow, then that ultrasonics right there. And then right here it's using the encoders to get a distance of the field. Then it rotates and it starts looking for this white line, and once it finds it, it releases the bridge. And here's crossing, and also that red line right there, it also follows it so it doesn't just fall off to the side. And here would be the team promotion, very fast, and then it hits the stop button. And this run would have gave us 89 out of the 120 points.
So for our competition results, first day we were doing qualifying round where we had 2 runs. For each of the runs we got 20 points, and in total we got 40 points, which placed us on the 18th place out of 53 teams. And we got in the semifinal round where we competed between 21 teams. And unfortunately our semifinal run did not go well, probably by Murphy's Law. We got only 10 points out, and it placed us on 19th place out of 21 teams. So here are our estimated cost analysis. So first of all, we were building the field material, competition field, and it was around $300. For our mechanical components, we spent around $200. For electrical components, we spent roughly $650. And also we spent $500 for Jetson or Nana, and almost $100 for Arduino Mega, which placed us around $1,700 for in total.
All right, so for further improvements, in terms of localization and navigation, the accuracy of the encoders can be improved. This could be done through closed loop feedback using a PID controller. Additionally, help out with orientation. Orientation sensor or IMU sensor could be used. This through sensor fusion with the encoder will help to circumvent any encoder error due to wheel slippage. Lastly, the object detection using a depth camera will help with determining the distance from the robot to the distance of the object desired. And lastly, image filtering to provide to reduce noise and attenuate the factors of interest, and thus making it more applicable to different light settings. Lastly, we'd like to thank those who supported us and helped us. Our organization, our IEEE Memphis Section Chair, Elizabeth Hayes, and the faculty, the Electrical Engineering Department, Dr. Welch, Dr. Ventura, and Dr. Baker, and the Benil Department, Mr. Motz and Mr. Rhodes, and our fellow colleagues, Abdallah Javaseh, Sergey Grigorev, Brendan Guerrero, Julian Weir, and Eileen Zavala. Take a picture. And any questions?
So you talked about further improvements. If you would have implemented all that stuff, how much longer would it take to build the robot?
It's like probably like another month.
Yeah,
Another month.
month or 2.
And then so out of all the stuff that you've got recommended right there, what one thing would improve you the most?
I'd say the PID controller, because we had a very big issue going up the ramps where we had wheel slippage. And also with that, the IMU sensor lets you know the orientation of the robot. So if it's at a slant, you could figure out if you're up the ramp, or you still need to keep, spinning the wheels to get up there. Any other questions? Yeah.
Would a tractor type of drive assembly be better than a wheel?
I don't know what you mean by that. Oh, like a tank? Like tank tracks?
Where you got a loop tread.
Yeah, that was something we saw a lot at the competition. There was a lot of tank tracks, and we did actually have that considered in the beginning. But we chose just 2 wheels just for be able to turn around the competition and pick up the little boxes.
So we're using stepper motors for your drive, or?
No, brushless gear motor. Any other questions? Yeah.
So like, just looking at that run, like the robot, or at least the motors look like they're turning super quickly. They're revving up really quickly, and like it's causing a lot of jerkiness in the robot. Like, do you think that could have been changed by just like adding some type of like current switches? Because I feel like
That was very easy to fix in the code. But we did that so we could get the fastest time. Because we're right at the cutoff time. We're at 1:44, and after a minute 45, you start losing 10 points. So we just grabbed it as fast as we could.
Why did you lose to the line following, yellow line?
We had 2 IR sensors on the bottom that we used ultrasonic sensors to position ourselves to where they would be, and then we would start following it. And if it goes off course, and it would tell it to, rotate this wheel a little bit faster than this one, so it orientates itself straight.
Why do you need 7 volts for the mega?
It was one just some voltage in between which we took. So because there was a certain range for voltage for doing the mega, so we took some medium one. I mean, we could use a lower one, but it was just
You can use 5 volt, right?
Yeah.
Mhm.
like
I think it was just so we didn't want to have all the components connected just to one singular voltage regulator to prevent current draw.
So totally you have 3 regular.
Initially, we were gonna use 3 regulators, but as regulators that didn't give us the necessary current draw, we switched just to 1 regulator, and basically what we did, just in Oro and Nano, it was powering Arduino Mega eventually, so in the end, yeah.
Alright.
So going off the voltage regulators, why do you think that it wasn't necessarily getting the correct amount of current in the first place?
So we tried different things, like we tried to reduce resistance or do other stuff, and the current draw was still the same all the time. And what my idea was that as this LM313 and 317, my bad, it has some inner current limitation, so maybe it was because of that, so it couldn't like heat up, for example, enough. Yeah, so for example, the regulator wouldn't go much in the heat up, so yeah, probably it was limiting the current, and that's why it was happening.
Thank you.